week 6 video lectures, we saw how to implement classes that allows us to create instances of a certain object. The most important property of object classes is encapsulation. That means that the object stores internal information that we can access without knowing the internal structure of the object. We also saw some nice examples in which we created instances of an object and updated the position through the use of internal methods and using the parameters of a given domain. In this video we are going to see how to create an environment that hosts some entities, but this is not going to be a physical domain that encloses the objects. Instead, it will be an abstract environment that tracks and has control over the hosted objects. We will also see how to interact with the environment ourselves. Similarly to what we've seen in the video lectures examples, our program runs an environment that in this case we call a biome, that is an instance of the class biome that has some internal information and some internal methods. This biome hosts a number of entities that are in fact instances of the class entity that also have some internal information and some internal methods. In fact, the biome does not really host the object's entity. The biome is an object that happens to be able to track the information of the entities in a list and that knows the methods to control these entities. Apart from the understanding approach, we could represent it this way, the biome in the same size of the elements. Here we've got the code that implements our biome. Here we can see that we have some helper functions that we are not going to stop at all of them, so you can see them by yourselves. And then we have the Biome class and the entity class. The first thing we are going to see is the entity class. This object class entity have some methods built inside. First of all, we have the constructor method that assigns some parameters to each one of the object instances created. For instance, here it uses a global parameter. Here it uses a helper function that gives a random speed, and we can see that it also gives to each one of the entities an identification that it prints as well in the console at each time we create a new object instance. We have the str, the move, that makes the entity move each time we call it and make it bounce at the edge of the canvas. We've got an update method that makes the circle of the entity a bit bigger. We've got the draw method. This is different to what we have seen in the lectures, because here, in order to draw each one of the objects, we have to call this method for each one of them, and the object prints itself. Then we've got some functions here to get the information, the internal information of the object. This is very important for the encapsulation. And finally, here we've got a method called collision that returns true if our object is colliding with another entity, another instance of entity. And what it does is, first of all, it discards the collision between the smallest elements, those whose radius are smaller than 8. We have made this in order to avoid a lot of computation. Then it computes the distance between the center of both elements. For the self entity, it just go and take the position with self that pose. But for the second, it uses the get methods. We can see here that how they are useful. And finally, it returns whether the distance that we have just calculated is smaller or not of the addition of both radius. If it is smaller, yeah, it's true, both elements are colliding. Next, we are going to take a look at the Biome class. The Biome class has some internal methods. First, we've got the constructor method. It simply implements two lists. First, a list of entities that the biome is hosting, and second, a list of combinations. That is a list of all the possible combinations between each pair of entities in the biome. We will see later how we do it. Then we've got the span method. We use it to create a new entity on the biome. What it does is it creates an object of the class entity with a given position with the name new entity, and then it appends this new entity to the internal list of entities, and finally it recomputes the combinations between all the entities. Then we've got three methods that make you indirect use of the internal methods of the entities. We've got the move that calls the entity move of all the entities on the biome, and only the entities that are in the self entities list. Another method that makes them update their size, and another method that makes them draw themselves in the canvas. And finally, we've got here the most complex part of all the code, and very important for running the program, but we will see after we have tested the program. I can tell you that we use this method to check if any of the entities are colliding, and if they are colliding, they are destroyed, well, they are eliminated from the internal list of entities, so they are not drawn anymore, and new entities appear on their place. Well, before running the code, let's take a quick look at what the frame does. Well, we implement a frame and we implement a biome, and each time we draw the frame, the draw calls the biome that move, they make the entities move, check the collision, and draw the entities on the biome. And also we have to note that we are implementing a timer that each 100 milliseconds it calls the biome update, so it makes the entities grow. And we have also implemented a mouse click handler. Here we've got, each time we click on the screen, it calls the span position with the position we have clicked, so a new entity appears there. So let's run the code. Here we've got the canvas. If we click on the screen, a new entity appears. Here the identification of the new object is 0, and it is constantly calling the move, the check collision methods, and the draw, and also the timer is making the size of the entity grow. Let's check what happens if I create a new object. Well, the new ID is 1 and the object starts growing. Well, that's what happens when two elements collide. The program is constantly checking if this happens, and if this happens, we'll see how we do it in the code. And we can create as many objects as we want. Of course, the computation is bigger and it could start to be slow. Well, okay, let's close it. Let's see what happens inside of the collision function. So the collision method, first of all, it creates a blacklist. Remember that we cannot modify a list that we are iterating. So for the elements we want to destroy, we have to add them to a list and then destroy them here. So for each one of the combinations in self combinations of pairs, if the combination collides, we do it calling the collision method inside of each entity with the indexes the combination provides us. If it is true that they are colliding for both of the elements, if they are not already in the blacklist, then append them to the blacklist. After checking all the collisions in the canvas, for each entity in the blacklist, if the entity has not already been destroyed for any reason, then remove it from the list or internal list of entities. And also for each element that has been destroyed, then make a new entity appear in a nearby position. Why are we using a loop for here? Well, because if the element destroyed is big, we create a number of entities, not just one. We compute this number by dividing the radius of the element by 10. And we have some mysterious thing here. How do we compute a nearby position to the entity? Well, through a helper function here. A nearby position, it returns a position in a random range close to this position, to the position that we provide, and we check also if the position is inside of the canvas. Now the combinations helper function needs a lot of computing power because it provides an exhaustive list of all the elements, of all the combinations between entities on the biome. So we don't want to call it each time we draw the canvas, but only each time we create a new element. That's it. The update position function that we've been using in the previous lectures were very light in terms of computing resources. We could have hundreds of elements bouncing on the canvas without problem. This time the check collision method requires a lot of computation because it has to check the collision between pairs of elements each time we draw the canvas. However, we could see how we can track objects using lists and how we can use internal methods of objects to compare properties between pairs of them.